This is part 9 of our Decision Trees series. Today we'll discuss pruning in cart decision trees. In the previous video, we explored feature importance in decision trees and used cross-validation to find the optimal tree depth. In this video, we'll take a deeper look at post-pruning, specifically a technique called cost-complexity pruning. We'll focus on the main idea in this video, and in the next video, we'll walk through how to perform pruning step by step. Before we dive in, let's think about why pruning is necessary in the first place. In general, as the depth of a tree increases, the training error decreases. However, the test error tends to go up. This is the classic sign of overfitting. The model learns the training data too well and fails to generalize to new data. To address this, we can simplify a complex tree by removing unnecessary branches. This process is called pruning. Now, there are two main approaches to pruning. The first is pre-pruning, which is what we did in the previous video. In pre-pruning, we set constraints such as the maximum tree depth before training and use cross-validation to find the optimal value. The second approach is post-pruning. Instead of restricting the tree up front, we first let the tree grow fully, typically until it perfectly fits the training data. And then gradually remove branches that don't contribute to generalization. Cost complexity pruning falls into this category. This algorithm was proposed by Leo Breiman and his colleagues when they introduced the cart algorithm in 1984. With that background in mind, let's now define the notation we'll use to understand how this algorithm works. To make this concrete, let's look at an actual example of a decision tree. This tree has 4 leaf nodes. As this is the tree before pruning, fully grown to perfectly fit the training data, each leaf node is pure, meaning it contains only data points of the same class. Here we use uppercase T to refer to the full tree, and lowercase t to refer to an individual node within that tree. Now, look at the region highlighted by the red dotted line. This is the subtree obtained by splitting node T3. We denote this subtree as uppercase T with a subscript T3, or more simply as uppercase T sub 3. This subtree contains 3 leaf nodes, T4, T6, and T7. Then, notice the smaller subtree inside the green dotted line. This is T sub 5, which is nested within T sub 3. It contains 2 leaf nodes, T6 and T7. Next, let's define the misclassification rate. We use uppercase R of T to denote the misclassification rate of a tree T, and lowercase rt for the misclassification rate of an individual node T. NT denotes the number of data points in node T. Uppercase N denotes the total number of data points in the entire dataset. And M denotes the number of misclassified data points in a node. That is, the data points that belong to the minority class in a binary classification problem. With these definitions, the misclassification rate of a node RT is simply m divided by nmt. In other words, it's the fraction of data points in the node that are misclassified. The misclassification rate of a tree T is defined as the weighted sum of the misclassification rates across all of its leaf nodes. Here, P of T represents the weight assigned to node T, which reflects the proportion of data points that fall into that node relative to the entire dataset. For example, node T5 contains 6 data points, of which 4 are blue and 2 are red. Since the majority class is blue, the 2 red data points are considered misclassified. Therefore, m equals 2, and the misclassification rate of this node, R of T5, is 2 divided by 6, which gives us 1/3. Since the total number of data points in the dataset is 16, P of T5 is 6 divided by 16, which simplifies to 3/8. Now let's apply this formula to calculate the misclassification rate of subtree T5. Since T5 has 2 leaf nodes, T6 and T7, we can expand the formula as shown here. When we compute each term, both leaf nodes are pure, meaning all data points in each node belong to the same class. So their misclassification rates are 0. As a result, the misclassification rate of T5 is 0. If node T7 contains 1 misclassified data point, the misclassification rate would be 1/16. This makes sense because 1 out of the 16 total data points is misclassified, giving us a misclassification rate of 1/16. Here, lowercase r of t is the misclassification rate of node T itself, that is, before splitting. Uppercase R of T, on the other hand, is the misclassification rate of the subtree rooted at node T, that is, after splitting. Since splitting a node generally leads to purer child nodes, uppercase R of T is typically smaller than or equal to lowercase r of T. For this definition, we referred to the following document. Now that we've defined the necessary notation, let's move on to defining the cost complexity function. The cost complexity function C of t is defined as follows. The first term, RT, is the misclassification rate of tree T. The second term is the penalty term, where this symbol denotes the number of leaf nodes in tree T. And alpha is a non-negative regularization parameter that controls the trade-off between the two terms. As the tree grows deeper, the misclassification rate RT decreases, so the first term gets smaller. However, a deeper tree also has more leaf nodes, which increases the penalty term. In other words, there is a trade-off between misclassification rate and complexity. Cost complexity pruning seeks to find the tree that minimizes this cost complexity function, striking the optimal balance between misclassification rate and complexity. Now, let's express the cost complexity for subtrees and individual nodes according to the definitions above. The cost complexity of the subtree formed by splitting node T is defined as follows. Using the notation from the previous slide, the first term can be expressed as shown here. Next, the cost complexity of node T itself is defined as follows. Since node T is treated as a single leaf node, the number of leaf nodes is 1. And therefore the penalty term simplifies to just alpha. Next, let's calculate the cost complexity of node T3 and subtree T3 shown on the left through a concrete example. The cost complexity of node T3 can be expressed as follows. The misclassification rate R of T3 is 4/12, and P of T3 is 12/16. With alpha equal to 0.1, C of T3 evaluates to 0.35. Next, let's compute the cost complexity of subtree T3 using this formula. Since T3 has 3 leaf nodes, T4, T6, and T7, we sum up R of T times P of T for each leaf node as shown here. Since T3 has 3 leaf nodes, the penalty term is 3 times alpha, which gives 0.3. Therefore, C of T3 evaluates to 0.30. Now let's visualize these two equations on a graph. The red line represents the cost complexity of the subtree, CT. And the blue line represents that of the node, C of T. The x-axis corresponds to the value of alpha, and the y-axis represents the cost complexity. Let's start with the blue line. This line represents the cost complexity of a single node. Since it has only one leaf node, its slope is 1. Its y-intercept is the misclassification rate, R of T. Next, consider the red line. This represents the cost complexity of the subtree. In this example, the subtree has 3 leaf nodes, so its slope is 3. Its y-intercept is the total misclassification rate of the subtree, RT. Now let's compare the two. When alpha is small, the cost complexity is dominated by the misclassification term, i.e. the intercept. In this case, the node has a larger misclassification rate than the subtree, so its cost complexity is higher. However, as alpha increases, the penalty on the number of leaf nodes becomes more important. Because the subtree has more leaf nodes, its cost complexity increases more rapidly than that of the node. As a result, the two lines eventually intersect. Now let's find the value of alpha at this intersection point where C of T equals C of T. Solving this equation gives us the value known as alpha star. So what does this value actually mean? Let's interpret it step by step. The denominator represents the increase in the number of leaf nodes when the node is split. In other words, this is the cost of making the split. The numerator represents the reduction in misclassification error achieved by the split. This corresponds to the benefit. Therefore, alpha star represents the trade-off between benefit and cost. If the alpha star value is small, it means the benefit is small compared to the cost. In other words, the split is not efficient. On the other hand, if the alpha star value is large, it means we achieve a large benefit with relatively low cost. So the split is effective. Therefore, splits with small alpha star values are considered inefficient, and those nodes are pruned to avoid unnecessary model complexity. This is the core idea behind cost complexity pruning. In this video, we covered the key idea behind cost complexity pruning. In the next video, we'll walk through how to perform pruning step by step.